To start off with, a little bit of background about Desktop Metal as a company. Desktop Metal was founded in 2015 by leaders in advanced, it says here, manufacturing, metallurgy, and robotics. The point here is that these guys are really, really smart. They're a bunch of guys based out of the Boston area. They have a ton of guys from MIT on their team. They've got a whole team of PhDs in each of these different areas of manufacturing, metallurgy, and robotics to come together to kind of take a crack at this metal 3D printing industry where they've seen some pretty large gaps in terms of market share that they believe that they can fill with these two studio and production systems. So like I was talking about, Desktop Metal sat down, took a look at the metal manufacturing market. Looked like it was about $1 trillion in metal parts that's produced annually, with current metal 3D printing techniques only accounting for about 1 billion. So there's a very large set of shoes to fill from metal 3D printing side of things to grab a lot more of that market share that's out there in terms of metal parts. The reason the current metal 3D printing industry is so small compared to the potential is that it's really just too industrial and too expensive for prototyping, and it's not really fast enough or low cost enough for mass production. So it's this kind of awkward in-between stage where you're not really using it for prototyping. The barrier for entry for mass production is just so high that the mid-level to even more high-level stuff, you really can't justify the cost of current metal 3D printing technology. So they saw these 2 bullet points off to the right here, and they said, all right, let's attack this on 2 fronts and see how much more of this market that we can grab and attend to. So today's metal 3D printers are similar to a lot of the old 1970s punch card computers. They work, they create metal parts just like these computers made calculations effectively, but the machinery is very large. It requires very highly skilled operators to operate. You need special equipment and facilities to be able to run these machines, very similar to the current metal 3D printing state of things. You need specialized operators, you need specialized equipment and facilities, and it's just very expensive, and it's a very involved process in order to get metal parts. So to take a crack at that, Desktop Metal came up with this studio system. So what you're seeing on the screen here is this studio system printer in the front and the furnace off to the right. So this is the system that is aimed around taking care of the prototyping side of the market. It's a fully office-friendly metal 3D printing system, so you're not going to have specialized operators, you're not going to have different EH&S requirements to be able to run these machines in your facility. It's fully office-friendly. So we don't have hazardous powders in this system like a lot of the laser-based sintering systems that are out there. If you're not familiar with those systems, because the metal particles are so fine, they can get up in the dust into the air. So your operators need a hazmat suit and respirators. You need explosion-proof buildings in case that fine medical particles ignite. There's a lot of safety involved. Changing over materials is very arduous and a whole process. Here, we don't have that. This is a fully office-safe system. There's no stress relief here involved like the laser systems. Obviously there's no dangerous lasers. There's no third-party equipment. You don't have the dedicated operators. They did a really good job focusing on ease of use for this so that anyone could really send a part to the printer and press print and have a part ready in full metal. Another massive benefit of this studio system versus powder bed fusion is the cost. We're looking at about 10 times cheaper once you look at all the operators and the explosion-proof facility and the material costs and all of that stuff. Our DM Studio system is coming in at about 10 times cheaper than traditional powder bed fusion system. So kind of the secret sauce behind Desktop Metal Studio system here is that it was designed around the metal injection molding industry. So that is a couple benefits there. The main one being that the metal injection molding industry is a mature industry, over 40 years of experience, over 40 years of material R&D research that has already gone into this industry that can now be applied to Desktop Metal's 3D printing process. So once they're getting up and running, and once they have that, they now have that 40-plus years of experience to be able to incorporate into their process and make it even better, even faster for consumers and for people out in the industry that are using this technology. So a little bit about the background of how metal injection molding works. It's somewhat similar to plastic injection molding, which I'm sure a lot of you are familiar with. a few slight differences that we'll cover here. So if you see over on the left, the first step is to create your feedstock, which is a mixture of metal powder and polymer binder. And this is varying on different types of material and different applications, but a general rule of thumb is you're looking at about 80% metal powder and 20% polymer binder. You're going to combine those into your feedstock. You're going to take your feedstock, just like plastic injection molding, you're going to feed it into your injection molding machine, and you're going to shoot your parts into your mold. So you need your mold tooling here. From there, once you get your parts out, they are in what's called a green state. So we're still just a mixture of metal powder and polymer binder. The parts at this point are somewhat fragile. I call them almost like a clay-like consistency. If you were to drop them on the ground, they would shatter. So they're definitely not metal parts at this point in the green state. So from there, straight out of the mold in the green state, we need to get rid of that polymer binder. So we go to debinding. So it's soaked in a fluid bath, which dissolves that polymer binder, pulling it out. The reason we want that is once we go to the sintering oven, if we left that polymer binder in there, you're going to get a lot of metallurgical impurities. Your part's going to look crappy. It's not going to perform how you want it to. So we really need to pull that polymer out before we go to the final stage, which is the sintering oven. So in the sintering oven, our parts are heated to just below their melting point, and at that point, the metal particles will pull together through different forces and start to shrink the part as we fill those voids that the polymer binder was in before. So we're looking at about a 20% shrinkage rate, and this is MIM industry standard stuff. And by the end of the sintering process, then we've got a almost fully dense, we're looking at about 98% dense part, full metal that's coming out of that sintering oven. So how is desktop metal similar to this process? The large differences being on the front end here. So instead of the feedstock pellets we were looking at before, Desktop Metal Studio System uses feedstock rods. So instead of pellets, we're looking at rods. It's the same 80-20-ish mixture of metal powder and polymer binder. Those rods are fed into the printing system. So it's a 3D printer. If you're familiar with Stratasys' FDM machines, it's a similar process there. We've got a nozzle that's drawing out our 2D layers, and then we're moving up in the Z direction to create our 3D geometry. The large benefit here being similar to other 3D printing methods, you don't need any mold tooling that we saw on the last slide. So you're very flexible in terms of geometry. Every single part can be unique. You don't have to have any kind of minimum run quantities, anything like that, because it is a 3D printing process. So from there, after we're done on the printer, that's, again, we're in the green state, and then the process carries very similar that the metal injection molding slide that we just saw. So we're going to our debind tank to remove that polymer, and then we're going to our sintering oven to create a fully dense metal part after that. So Desktop Metal here has created a fully end-to-end system. You see in the middle there is your printer. On the left is the debinding station, and on the right is the sintering furnace. And this entire fully end-to-end system is office-friendly, classroom-safe, all that good stuff. You don't need any, like we went on the slide, you don't need any hazmat suits. You don't need any special facilities. All this can be in your office. So we're going to take a look at each of the individual of the three pieces of equipment a little bit closer. First, we're going to look at the Studio System printer. So like I said, it's very similar to one of the most widely used 3D printing processes of FDM. It's been around forever and it's following familiar design guidelines there. And again, we're looking at office-safe materials. We don't have any powder handling. We're just handling those rods. Your build size is looking at about 12 by 8 by 8. That is the actual build size of the printer. If you remember that I had talked about our parts shrink when they come out of the sintering oven. So in practice, the actual parts you can get off of this machine are more about 9.5 by 6.5 by 6.5 inches roughly after you account for shrinkage. The resolution you can get off this printer is about 0.02 of an inch or 50 microns, and then you can see we're printing at a speed of about 1 cubic inch per hour. So here's a look at the material bays in the top of the printer. So a big thing that Desktop Metal saw as a pain point in the current metal 3D printing industry is to switch over in the powder-based systems is a huge pain. You have to clear out all the powder in there because it's just loose powder. You have to make sure it's totally clean, that there's no contamination, all while in your hazmat suit and in your explosion-proof facility. So here they've come up with a very, very easy quick change cartridge. It's just you take that canister of 17.4 pH, which has those rods that we saw before, and it's a click in, click out, and that's how quick material changes are with this versus a potentially hours or even days process with a powder-based system. So here we're going to take a look at the process flow once we get our part off the printer. So we're printing off this small propeller part here. And then from here, again, we're in the green state. We're going to need to go, we can do a little bit of part finishing in this state. So like I said, they're almost like a clay-like consistency here. So something very nice that you can do is you can use sandpaper, or we've even found that something like a Brillo pad works even better to be able to pull that material away from the surface. And you can do part finishing in this green state. So you're actually hand sanding metal parts that you'll get a really nice surface finish once you come out of the sintering oven. From there, we go on to the debinder. So it's a low emission design. The big thing here is that, one, you will never see the fluid in this process. So you open that up to put your parts in, it's totally dry. The software will tell you how to arrange your parts to get the most efficient use of your debinding fluid and debinding time. Then you close the lid, it goes through its debinding cycle, and when you're done, the parts are totally dry and you take them out. So again, shooting for that office-safe environment, as well as it has automatic fluid distillation. So you're not going to be continuously replacing that cleaning fluid. It'll go through a distillation cycle, it'll remove that solidified waste into a canister in the back, and then you'll be able to reuse a large portion of your cleaning fluid, and you'll only have to top off every once in a while. So that's a nice feature as well. So here's a little graphic about our debinder. And from the debinder, then we head on over to the furnace to get our fully dense metal parts. So taking a look at the furnace, again, we're really looking at an office-friendly sintering furnace here. And this, I mean, the printer is really cool, the debinder is really cool, but like I said, they've got some really, really smart guys on their team, and this just kind of goes to show how smart and the different very cool things that they've done in terms of technology to be able to get a safety sign-off on this furnace that can reach up to 1,400 degrees C or 2,500 degrees Fahrenheit that can be right next to your desk and has safety sign-off from UL. So that just kind of goes to show you the kind of team they're working with there to be able to pull this off. It fits through the door. And another large benefit is you don't have any residual stresses like in laser-based systems. So you always have to heat treat in laser-based systems, and as well as while you're printing, if you're printing somewhat larger parts, because it's heating unevenly, it's drawing the surface out. Maybe the left side of your part is hotter than the right side of your part as you're building up in layers, and that can cause some warpage issues. But because we're heating all in one shot here, we don't have any of those residual stresses. We don't have any warping issues, which is another benefit of this kind of a system. So the furnace has expert metallurgy built in. So I've been saying that Desktop Metal has really been shooting for, you don't need expert operators to run this. You don't need a PhD in metallurgy. You don't need to know the metal injection molding industry really well to be able to get good parts out of this. So the furnace will actually take the files that you give to it, that you load in there. You tell this is what I'm loading into the furnace, and it'll give you a customized sintering profile to give you the best part quality as well as the fastest sinter time. So this is something that normally you would have to have that industry expertise to be able to pull off, but because they've built that into the furnace, all you really have to do is load your parts, tell it what it's loading, tell it what you're loading into it, and then press go, and it's really good to go from there. So when everything's said and done, we're looking at producing near net shaped parts with this process. So it's very similar to what you would consider in terms of accuracy of FDM-like parts. So they're very accurate, but they're not super accurate. They're more near net shape. And we are able to achieve density similar to the metal injection molding, so we're hovering around 96 to 98% dense depending on material. These parts are mechanically performing in initial tests very similar to their wrought alloy counterparts. You can see down on the right there, we have a cast part on the left from Caterpillar and a 3D printed part off the Studio system of the same geometry, and they performed almost identically in mechanical testing. So we have a wide range of materials to choose from because we are designed around the metal injection molding industry. So here's a look at what materials we currently have available on the left. So we've got 6 different stainless steel, high strength alloys, tool steels, high corrosion resistant stuff. And then on the right, we've got a bunch of different stuff. So everybody's always wanted to know, when are you going to get aluminum? When are you going to get titanium? Those are 2 of the materials that are highest on their list. And they expect those materials to be out within a year and everything else to be out within 1 to 3 years after a release date. So they're really cranking on these materials. And like I said, they've got that 40-year head start because they are piggybacking on the research of the metal injection molding industry. Another huge benefit of the DM Studio system over laser-based systems is hand-removing supports. So you can see on the right, this is the basic process for removing supports on the metal system. This is achieved by, when we're printing these supports, we're laying down a thin ceramic interface layer that actually turns to dust in the sintering oven, which allows us to just very easily pull these parts apart by hand. Whereas on the left, you can see this is a build tray off of a laser-based system. The supports here are not only welded to the build tray, but they're welded to the parts as well. So you're cutting your parts off your build tray, you're cutting your supports off your parts, and then you're probably going back with a grinder or some sort of an abrasive to improve the part surface quality on the underside of those parts. So it's really a labor-intensive process versus the desktop metal is really just kind of a pop-off process. So again, this is a fully software-controlled workflow. So you load a file into the printer, and the cloud-based software follows it along the entire process from debinding station to furnace. So you print a couple parts off the printer, then you're probably going to end up batch loading into the debinder. You're going to tell the software what you're going to load into that debinding station. It'll tell you how to arrange the parts. Same thing for the sintering oven. You're going to load some parts in there. It'll tell you how to arrange them. A lot of benefit here is it's a fully automated system, so you don't really need to know too much about what's going on. It's very user-friendly. We're supportive of native CAD file types. You can drop in your SolidWorks file. You can drop in STEP and IGES files. You can drop in Inventor file, things along these lines, and just go straight from there without any need for any kind of an STL file. And then we do want to mention it is cloud-based, but we do have remote or local cloud options available. So if your industry, maybe you're in the military or aerospace industry where you can't have a cloud connection to an off-site connection, you can get a local cloud available that you can kind of keep wraps on and keep on your property and work through whatever needs that your industry has. So we were just taking a look at the Desktop Metal Studio system, which was focused on metal 3D printing in terms of prototypes. Now we're going to take a look at the still in development Desktop Metal production system. So here, what the goal was, if you remember from one of the first slides, is that current metal 3D printing techniques are too slow and they aren't cost effective enough for mass prototyping. So they're actually able to come up with this machine that is about 100 times faster and 20 times lower the cost than current metal 3D printing technologies. So it's powered by this technology called single pass jetting. So essentially what we're doing is we have a print head similar to some other binder jetting kind of 3D printing, if you're familiar with that. And every time the head moves, it's able to print a layer. So back and forth, that's how they're getting that high throughput. So it was created by the inventors of the binder jet and single pass inkjet. So those guys came together and really, this is their brainchild in order to get that goal of super high efficiency and super good throughput and cost reduction. We're looking at a build area of about 13 by 13 by 13 inches. Our resolution in terms of voxels or 3D pixels is about 2/1000ths of an inch or 50 microns per voxel. And then here is kind of where we're looking at the terms in volumetric rate here. We're looking at 500 cubic inches per hour off of this machine, which is just really kind of a huge testament to show what their really goal is for mass production with this thing. So here's what they've kind of done their preliminary calculations. Because the printer is so fast, it requires a couple of furnaces to keep up with it. They're looking at about 4 furnaces per production system. But with that fully loaded out system, you're looking at about 10,000 cubic inches per day per printer, which is a really crazy amount of metal material to be able to push through your facility in a 24-hour period. You're really going to start chewing into the casting industry and start getting there. As we look, it's about about 100,000 parts. We'll see a slide coming up where the break-even point between traditional casting and this 3D printing is, because it is such a high throughput and low-cost system. So again, comparing to the laser-based competitive systems, the current parts are welded to the bed. So not only are you, again, having to manually remove those supports, but you are limited to only a single layer of parts. DM production is able to do a fully packed build volume. So you are able to use the full 13 by 13 by 13 build tray available and really pack parts in there. So you can see that's a full assembly there on the right, as opposed to having to print each part in a batch and print 10 or 20 or 100 of them at a time. You can print your full assembly all in one go, and you can go from there. So really a huge advantage in terms of flexibility of manufacturing. So here again, we're taking a look at the competitive cost per part, comparing laser powder bed fusion, traditional casting methods, and DM production. So because we are able to hit that really high number of 500 cubic inches per hour, the calculations show at about 100,000 parts is where your break-even point for casting versus DM production. So if you're making less than 100,000 parts in a run, you might want to consider a DM production machine, as it'll give you a better hold on cost and a better reduction in material costs and throughput and things like that. So obviously, just like other 3D printing methods, the traditional mass manufacturing is going to win out over the millions of parts, but at around 100,000 is pretty good for a 3D printing production system, in my opinion. So like I mentioned, this desktop metal production system is still in development. They have working prototypes, and they're going through, and they've gotten some great parts off, but they're just ironing out the kinks at this point, and they're scheduled to be shipping in Q1 2019. So to kind of sum up here of what we just looked at, desktop metal is attacking that gap in the 3D metal printing market on two different fronts. They're covering the prototyping with the first system we saw, the Desktop Metal Studio, and the mass production with their Desktop Metal production system. So a more in-depth look, we've got our studio system on the left. Its print technology is bound metal deposition, so that's kind of similar to that FDM process that we saw. It's office friendly. It uses the bound metal rods that we were looking at, and they're just about ready to get shipping in a couple months here. We actually have here in Buffalo Grove, we have our beta machine that we're going through testing with Desktop Metal and giving them feedback, so we're almost up and running there. And then on the right, you have the production system. It's aimed at mass production. It's powered by the single-pass binder jetting system. It's definitely for an industrial environment. It is a power-based system, and it's still in development. We're looking at a 2019 release date. So at this point, we're going to open it up to questions in the chat, and we're going to go through and see what kind of questions you guys can come up with.
So everybody, if you could message the CATI user the questions. I don't know if you had any come up on your side, Colin. I have a few on this side. Did you get any?
I'm trying to see where my chat box went.
All right. So while you're looking, somebody is asking about the materials, which you went over that a little bit, but they're also asking about combinations of materials. Is it possible to mix materials in probably all three processes? The printer, can you mix materials in the debinding station and in the sintering furnace?
Okay, so I actually have had that question quite a bit. So currently they are looking into what they can do for that. It's not super high priority at this point, but to be able to print, physically printing them, it wouldn't be so much of a challenge to print like a layer of a steel, then a layer of aluminum, something along those lines. But when you get into the furnace, materials sinter at different rates, so you're going to have a bunch of different conflicting sintering profiles with the different materials there, so it's really a very difficult engineering challenge on their part that they are looking into, but it's not super high priority at this point. So to answer your question currently, no, you cannot print in multi-material prints.
And then what would that process look like if you wanted to have different parts and different materials?
So if you wanted to have different parts and different materials, you're going to need to have them in separate batches. So first thing you would do is on your printer, like we showed with the quick change cartridges, you're going to change over to your two different materials. So you print in steel first, you got a couple of parts there, and then you want to start printing in aluminum. Those batches are going to need to be totally separate. So all your steel parts are going to go to the debinder, then all your steel parts are going to go to the furnace, totally separate from your aluminum parts that are going to have their own batches of debinding and sintering.
And is there any cleanup process in the debinding station at all that you know of?
In the debinding station, no, there's no cleanup. It's just a soak, and then it dries it, so you're just pulling out these parts after they've been debound and putting them over to the sintering furnace.
Okay. So the next question is they're asking about if the debinding fluid, I believe they're talking about, is toxic. Have you heard what that fluid is yet?
I have an SDS sheet. I have to look and find it. It's not something that they wanted the average user to be exposed to. That's why they go through the full drying cycle before the parts are released to the user to maintain that office-safe environment. I'm not exactly sure how unsafe it is. It is fully sealed off, and then the waste goes into the waste tank that you do actually need to have some sort of a waste collection agency come and take that away. So it's not able to be just thrown away through normal means. But the waste tank is maybe like a gallon, and they're projecting that it'll be like 8 to 12 months that you're going to need to change out your waste tanks, because you're only soaking out that binder, and it's a very low volume of waste there.
Okay. Another question is around the cost of the consumables, so rods, the fluids, the interface material, and then there's a couple questions on the price points of the studio system as well as the production system. Do we have any like rough numbers, or is that something more of a salesperson should answer?
So I can give you rough numbers. If you're looking for exact numbers, please reach out and contact some of our sales folks, and they can get you more exact stuff. But to give you a ballpark in terms of material, so the lower end materials like the 17.4, the 316, you're looking at around like $8 to $9 a cubic inch. The higher end materials, as you saw, we had like Inconel, some super alloys. Those are getting up into the $30 to $40 a cubic inch range. So depending on what you're trying to print, if you're trying to do those super alloys, it is going to be a little bit more expensive, because the process to make those powders and the binders is a little bit more intense. The interface is actually one of the more expensive materials, at around, I think it's like $60 or $65 a cubic inch. But if you noticed on the print, I can bring it back up here. Let me pull it back up. We're really only using a layer or two between the support surface and the part surface. So you're never going to use anywhere near a cubic inch on any print. You're going to be down a tenth of a cubic inch, even less, because it is only the 1 or 2 layers to relieve that support face from its actual model face during the sintering phase. For the cost on the system, the DM Studio system, once everything's said and done in terms of installation and maintenance contract and shipping and all that good stuff, you're looking at about $150K to your doorstep. The production system, I haven't heard any prices quoted. I'm not sure if the sales has more relevant information than I do, but I haven't heard any prices quoted there. But it is going to be, I would imagine, significantly more expensive than the studio prototyping system, just because it is a much larger system made for a heavy-duty production environment.
Okay. So this sounds kind of like almost like somebody that might be involved with the current MIM industry. Is there a part thickness limitation for the debind operation?
Yes, exactly. So we can do and this is a MIM industry limitation. It's nothing to do with the desktop metal process. It's about 6 millimeter wall thickness. So you can have a shell on your part of about 6 millimeters with some of the honeycomb infill in the middle, or you can do, if you were to butt up 2 6 millimeter walls together to create a 12 millimeter solid part. So you can do 12 millimeters solid in any direction, and once you get past 12 millimeters, you need to break it into 6 millimeters infill and 6 millimeters. And the reason for that is the debinding fluid can only penetrate so far given a certain amount of time that's reasonable. So 6 millimeters is about that sweet spot where we're starting to get into the realm of we're just kind of spinning our wheels in the debind tank if we go thicker than that.
All right. Another question is, are high carbon steels available? And there may be more. I'm only halfway through the question so far. There may be more material questions. Can you bring up that slide that had all the materials?
Yes.
And while you're doing that, is a respirator or some sort of breathing mask recommended to sand the green part?
It doesn't really get it. So it's more the metal powder. It's the metal powder with the polymer binder, and it doesn't really get airborne that much because they are much larger particles than the powder-based processes. So one of the nice things about this desktop metal system, here's our material slide. We're able to kind of use the reject powder from the laser-based systems. The laser-based systems need really, really fine, really, really consistent particle size, whereas this MIM-based process can use some stuff that's a little bit more varied and a little bit less precise of a powder size. So that combined with the polymer binder in there, it doesn't really get up in the air at all. It really just clumps up and falls off because it is that dense metal. So it's not like sawdust or anything where it'll get in the air and get up there. It is heavier and it'll fall right away. So you don't need a respirator with that.
Okay, perfect. So another question here on finishing processes. So once you have your part sintered, you pull it out, you got all the support removed, can it be treated as a normal part? As in you can machine it, you can plate it, you can passivate it?
Exactly. Anything that you could do to a cast part, you can do to this. It's almost essentially the same thing. So any kind of finishing, any kind of post-processing that you do to a normal metal part, you can do the same thing to this.
Okay, perfect. Another question here is how well have you found the geometry after sintering to be compared to the CAD dimensions? Like what's the accuracy like after sintering?
So the quoted accuracy, and this is actually something that we at CATI are kind of interested in as well. We also sell 3D scanning systems for inspection purposes, so we're kind of double dipping there. We're using our scanning equipment to scan up the parts after they come out of the sintering process to take a look. What the parts have been quoted at is very similar to FDM systems, so we're looking at about plus or minus 200 microns. And what we found is they're within that. In some cases, they're well within that range, but we haven't found anything outside of that range. But yeah, we're interested in that as well.
Awesome. So the cloud option, the local cloud, is that something in development? What's the release date for that?
I believe it's already, at this point, everything is still in development. We're still working through, like I said, we have the beta machine here for the studio system, and then the production system is still even in further development. So everything's subject to change at this point, but I know that they do have some customers that were specifically requesting that because they were in the military or aerospace applications, and I believe that they did go through and create those local cloud environments for them to do testing as well. So that's something that is there, it exists. Can I say that it's set in stone at this point? Definitely not. I'm sure it'll change based on feedback, but it is there. It's not something that's off on the horizon.
All right. So this is a good question. So if you have a part with like cooling channels, like conformal cooling channels inside of your part, how would you remove the support structure?
So the software actually goes through and creates extra interface layers. So if you're imagining a cylinder, it wouldn't just put interface around the outside of the cylinder, especially for complex internal channels like that. It'll actually chop that cylinder up into a bunch of little pieces so that when that ceramic turns to dust, it'll just be a bunch of little shattered pieces of metal that'll come out, and it'll be much easier to remove.
Okay. Let's see here. Surface finishes. Do you have any idea on the surface finishes that you could expect after getting sintered?
They're going to be very similar to cast parts. So they're not going to be amazing, but they're going to be very similar to cast parts.
All right. So here's another good question. I've been asked this one a little bit. Going through the debinding stage, you're removing some of the binder. What's holding the parts together? Are they very brittle at that point?
They are very brittle. It's actually a secondary binder. So the first binder is a polymer-based binder that's stronger and makes up a bulk of the binder. The secondary binder is a organic wax-based kind of a binder, and that burns away in the sintering furnace and doesn't affect the metallurgy at all, but it is a much weaker bond. So once you go from the debinding to the sintering furnace, the parts are much weaker.
Here's another materials question. Will there be any need for further post-heat treatments after tool seal material, after the tool seal materials are sintering? And then the second question, do you have any information regarding the as-sintered hardness of these materials?
I don't have too much information on that. I know they're going through and they're still doing a lot of testing for different case studies. That has come up quite a few times before. Once you get it out of the sintering furnace, you don't need to do any extra heat treating, but it's definitely something that you can do if you're trying to achieve higher hardnesses.
Okay, so you could just treat it like any other tool seal that you would normally have work with, right?
Exactly, yeah. So they're trying to get some documentation on that.
Okay. Here's another material question is when will copper be available? Do we have any timeline on that?
I think that's like third or fourth on the list behind aluminum and titanium. So it's definitely high priority there. And like I said, they haven't really given super specific dates on those. They're staying aluminum and titanium within a year, and then everything else within 1 to 3 years. So it's not out yet, but it's on their radar.
Okay. A couple more questions on parts coming out. Do we have to design in the part shrinkage for the material, or does the software compensate for that?
Software compensates. So you design your 5-inch part. A 7-inch part is going to come off the printer, and then once you sinter it, it's going to shrink back down to that 5 inches.
Okay. Another question on the part. So if you were to print a cup, let's say, would that cup be watertight, or if you were to do a channel in the part, would that hold pressure at all? Is there any porosity that would not be airtight in these parts when they come off the sintering furnace?
So there is, I don't want to say there's no porosity, there's some micro porosity because we are around that like 98% density range, but they are watertight parts because it goes through that shrinkage and that sintering process. We don't have those voids, those large voids like normal FDM plastic parts have. We do actually have watertight surfaces. So they just released in an injection molding case study that kind of touched on that a little bit, and we've got some good demo parts that kind of show once you machine down that surface to the naked eye, it looks almost exactly like just a normal metal part. You can't tell any porosity or anything like that.
All right, so it looks like the questions are slowing down. One more here is somebody put in an order today. When can they expect delivery? And then when are they going to start shipping in general? The studio system.
The estimated start shipping is 3 to 4 months from now is what they're looking at. So they encountered some different feedback things during this beta testing that they want to get out and really iron out the kinks before they do start shipping. So I know people have been really eager for this and they want it now, but Desktop Metal is, in my opinion, doing a really good job of, we want to make sure it gets a good product out there before we go, and it's really our flagship product, so they want to do a good job on the first time. So they're looking at 3 to 4 months. I'm not even, I know you can do reservations. I'm not sure if they're taking orders at this point. I think you can, but I know they can do reservations.
Gotcha. All right. Well, give you a couple more seconds for any last minute questions. There will be, in the past on these presentations, they've made these available on YouTube. I'm assuming that they'll do the same thing with this one. A couple people have asked for the presentation in general. I think the PDF could be made available as a download. I'm not sure how that'll go out, but we can make that happen, I think.
Yeah, that should be no problem.
So what's the sample parts? Like if somebody wanted to buy the system, are we able to do a benchmark?
Yeah, so with your reservation, for the studio system, I believe it's $1,000. For the production system, I think it's $5,000. With your reservation, part of that process, you get a benchmark part. So you send in the part, and we'll print it out for you. We'll talk through the application and see what kind of settings work best for your application, and we'll get you a metal part once you have that reservation in.
Okay. Somebody came in late and missed the cost, the ballpark price for the consumables and the systems. Do you want to cover that again?
Yeah, no problem. I'll do it real quick. So your lower end materials, so you're looking at some of your stainless steels, things like that. You're looking at about $8 to $9 a cubic inch. Some of your higher end materials, like if we've got the Inconel on there, I know that's around like $30 to $40 a cubic inch. So we're bumping up quite a bit in price. And then your ceramic interface is going to be a little bit even more expensive than that, around $60 to $70 a cubic inch. And I just wanted to mention again that the interface layer is just a two-layer interface between the support structure and the model structure. So you're really never going to be using anywhere near a full cubic inch for most prints. So it is higher cost, but really you're not using almost any of that material. For the actual systems themselves, the DM Studio system, once everything's said and done with shipping and installation and all that good stuff, you're looking at about $150,000 shipped to your door. And then the production system, I haven't heard any quoted prices or anything like that. I'm not sure if sales has any information that we haven't heard yet, but I've yet to hear that. But it is, again, it's much more in R&D, and it's not scheduled to be released until 2019.
Okay. Any word on other consumables like filters, debinding fluid? Do we know anything about that yet?
Debinding fluid, I would have to check on. I know that there are some inert gases that need to be used for the sintering oven. So currently, you're going to be using the desktop metal gas that will have to be as a consumable. I believe those tanks, to run a sintering cycle, you'll need about $200 worth of gas to run that cycle. And they are looking at being able to incorporate different house gas that you have on your shop. But there's going to be a process that they want to go through and make sure that there's not going to be any way that anyone could hook up the gases backwards or wrong or anything like that and cause some sort of an accident. So they want to just hit the ground running with this desktop metal gas canisters that they know is good and know is going to work right and is foolproof in terms of safety. And then once they get running, they're going to look at a program to validate people's house gas setup and be able to use their own house gas.
Gotcha. All right, I'm just scanning through to make sure I didn't miss anybody. There was a lot of good questions here. Someone was asking, is it possible to get a sample part without paying that $1,000 reservation fee? Or is that possible? Do we know?
Yeah, currently it's not. There's a large backlog of demand of these benchmarks, so there's a huge priority for the people who have had put in reservations. Once that dies down, I don't see why we wouldn't start doing benchmarks for other people, but I don't see that demand for reservations and benchmarks dying down anytime soon.
And they'll knock that $1,000 off the price of the system later on, right?
Yeah, so it goes towards not just the burn $1,000, it goes towards, so then you pay $149 for the system, or whatever it ends up being.
Gotcha. All right. Well, I guess if any further questions come in before we shut down the recording, we'll try to maybe send those out later on. I'd like to thank everybody for showing up today and learning about desktop metal. Thank you, Colin, for the awesome presentation. Everybody have a good day.
Thank you for monitoring, Henry.